Okay, so Stokes 10, I mean, this problem is largely about drawing the right picture and making sure you understand the geometry of the setup. And then we're just going to apply one of Maxwell's theorems, and but there's a lot of details in it. So, okay, we've got a steady state current through a wire on the z-axis. All right. So there's our z-axis. We've got a steady state current through this wire on the z-axis. Like so. Okay, now at a nearby point x, the magnetic field created by this current points in a direction that's tangent to a particular circle. Okay, so first let's talk about the circle. Forget about the whole magnetic field business. Let's talk about this circle. It's a circle centered on the z-axis that's parallel to the xy plane and passes through the point x. So, for example, let's take that point x there. I claim that there is a unique circle that's centered on the z-axis, parallel to the xy plane, that passes through that point. And it's going to look something kind of like this. So, does that make sense? And you see how there's only one circle that does this? Okay. So now the problem says, at such a point, the magnetic field created by this current, the magnetic field points tangent to that circle. So the magnetic field is going to be that way. Is everybody on board? Okay. All right. So the problem says now show the magnitude of the magnetic field is inversely proportional to the distance from that point to the wire. Okay, fine. All right. Now the hint is that what we're going to follow. It says let's compute a line integral of the magnetic field around this circle, and let's just kind of see what comes out of that. Right. Okay. All right. So computing that magnetic field. That line integral of that magnetic field. So the line integral, by the way, this curve, note that curve is the boundary of this that I might call the surface S, right, oriented up, let's say, because I want this curve to be going counterclockwise as seen from up. It's my surface. I can set up any way I want, right? So I'm going to set it up. Okay, so we want to do an integral b dot dx around that curve. Well, of course, this is a line integral of the magnetic field around a boundary of a surface. So I can rewrite this as, in fact, I don't even need to use Stokes' curl theorem, but the corresponding Maxwell's theorem tells us that this is going to be mu naught times the current, right? Everybody happy? So it's the same Maxwell theorem that we used in the previous example, or in let's see, it was problem 8, I guess it was. So, the current is known. I'm just going to leave it as I. Of course, that's just a constant. Now the question is, what else can we do with this? The problem. The hint said to compute this line integral. How is that going to tell me something about the magnitude of the magnetic field? So I've got to figure one of these things is going to have to relate somehow to the magnitude of that B field. And I claim it's going to be this integral here. Because I can rewrite, this is a line integral, a la chapter 5, and I can rewrite this in a couple of different ways. One of them is I can rewrite this as integral around the curve of B dot unit tangent vector ds. Right. Is everybody good? So remember, there's this unit tangent vector that's pointing tangent to the curve, like that. Now, dot products I can rewrite. Of course, this is length of B, length of T, cosine theta, d little s. Right? Dot product. Formula for dot product. Now, good news. This is a unit tangent vector, so that here is just 1. What about the cosine of theta? Well, where's theta? Theta is the angle between these two vectors. Now, one of the critical givens in the problem is that the magnetic field was tangent to the circle, just like the t vector is, of course, by definition, tangent to the circle. So that means that the angle between these two vectors is 0. And if that angle is 0, the cosine is 1. So what we have then is that the line integral around this path of length of b ds is what this line integral, this vector line integral here is equal to, which of course is mu naught I. And we'll get back to that in a second. The last step is to say that, well, look, the magnetic field that's created by this wire is going to have the same length all the way around. Right? That's just a symmetry argument. If you were to take that wire and just rotate the wire around the z-axis, well, nothing happens. But as you rotate, that would have to rotate the magnetic field. That means that nothing can happen to the magnetic field either. So just by that symmetry argument, this is a constant around that entire circle, which means that this is length of b times, and then just integral over the curve of 1 ds. And this, of course, is just the length of the curve. Is that cool? So what I have then is that mu naught I is length of b times, and well, the length of this curve, that curve is just 2 pi r. Let's let r be the radius, right? So 2 pi r. And therefore, I can solve for the length of b in this equation. I kind of ran out of space here. Let me just squeeze it in right here. The length of b is mu naught I over 2 pi r. And you see there it's inversely proportional to r. Does that make sense to everybody? So, I mean, again, there's a certain amount of setup in this problem, and a large part of what makes this problem difficult is geometrically interpreting what the problem says about how that magnetic field points, right? And then we write down Maxwell's law, the corresponding Maxwell's law, and as hinted, and then we just have to make the realization that this line integral is going to relate to the length of the magnetic field by way of this involving a dot product with the magnetic field, and lucky break, the length of the magnetic field just kind of shows up in the calculation and ends up being something we can write down easily. Yeah. Okay. Questions? So this is a hard problem, by the way. This is definitely intended to be a tough one, but now that we've made it through the problem, I hope this makes sense. Okay. All right. Nobody has questions? I'm kind of surprised. Feel free.
Can you just go over again why the cosine theta is 1?
Yeah, right. So remember in the statement of the problem, let's see, the magnetic field points in a direction tangent to the circle. Right, so that says that this B field is pointing tangent. Well, this T is by definition tangent to the circle. It's a unit tangent vector. So these are both tangent to the same curve, therefore they're parallel. Yeah, sure. Anybody else?
So what sort of technique were you using when you decided to multiply by the unit tangent vector?
Oh, this here?
Yeah.
Well, so in taking this step here, I didn't really so much multiply by the unit tangent vector, but this is just an alternative formulation. If you look back in Chapter 5 when we define vector line integrals, there's 3 different ways that we talk about how to, well, 3 or 4 depending on, anyway, several different ways to write down vector line integrals. And specifically this dx, you can rewrite dx as unit tangent vector times scalar length element. So dx equals TDS is just a pat formula from Chapter 5. And how do you know when to do that? Well, it really depends on the circumstance. And I wanted the length of this to show up, and I know that length of vectors involved in dot products show up when you actually expand that dot product in terms of, well, the length of the one times the length of the other. I just needed another vector to put here. So it was just convenient for me to rewrite dx as TDS. That's all. Yep. Okay, anybody else? Feel free. It's a tough problem. Yeah.
How did we put out the D again?
I'm sorry?
How do we get D out? D out?
How do we pull this out to here?
Yeah.
Because I made a symmetry argument about how the length of the magnetic field has to be the same no matter where you are around this circle. So, for example, let's suppose you're looking at this situation. You've got this current through the wire, right, and that's creating a magnetic field. We're given that it's always tangent to this circle. In other words, wherever you are on the circle, the magnetic field is always tangent, like that. So I claim that if we were to take the whole picture and rotate it, then everything rotates. The wire would rotate around the z-axis. The magnetic field correspondingly would rotate because it's a real physical thing. If you pick the whole thing up and rotate it, everything has to rotate. But critically, when you rotate that wire around the z-axis, nothing happens. So what that means is the magnetic field, as you rotate that magnetic field sort of around the z-axis, nothing happens. And that means that the length of the magnetic field is the same all the way around. So it's a subtle point, but this is a true fact about this situation. Does that make sense? Yeah, it is subtle. Absolutely. Yeah. Anybody else? Okay. All right, let me wrap this up.